In this question, we know that the x is uniform in A to B. And so we can write the probability density function as this expression. And we can also draw the figure of probability density function as this. And because the probability distribution function is the integral of the probability density function, so we can calculate the probability distribution function using the integral of the probability density function. So we can write using the probability density function, we can write the probability distribution function as this. And it's obvious that when x is smaller than a, it is obvious that the probability density is 0. So the probability distribution when x is smaller than a is 0, and when x is between a and b, and the distribution function is we need to calculate the integral of 1 divided by b minus a multiple t, integral from a to x. And when x is bigger than b, it is obvious that the distribution should be 1. And so we can calculate the result. And when x is between a and b, it equals to x minus a divided by b minus a. And when x is bigger than b, the probability is 1. And so we can draw the figure of capital Fx. And the probability should be the probability distribution function should be like this. And this is a question. And the B question. In the B question, we know that the capital Y is equals to the capital X to the power of 2, and because the capital X can get value from the statement in the question, we know that a equals to -1 and b equals to 3, so x can get value in -1 to 3, and so the y can get value from 0 to 9. And so it's obvious when when small y is less than 0, it is obvious that the capital F y y is equals to 0 and the smaller f y y equals to 0. And when y is bigger than 0, 0, we can write the probability distribution function in this capital F y y equals to the probability of capital Y smaller or equals to Y, and this equals to, and because capital Y equals to x, capital X to the power of 2, so it is equals to, and this can equals to p minus y to the power of 1 divided by 2 and capital X is between this, and this is equals to capital F X y to the power of 1 divided by 2 minus capital F X minus y to the power of 1 divided by 2. And because when a is equals to minus 1 and b is 3, so it is obvious that when y is bigger is greater or equals to 0, it should be divided into 3 circumstances. First, when y is between 0 and 1. In this circumstance, capital F y y equals to capital F x y to the power of 1 divided by 2 minus capital F x minus y to the power of 1 divided by 2, and this equals to 2 multiple y to the power of 1 divided by 2 divided by b minus a, and because b is equals to 3 and a equals to minus 1, so this equals to, and this is when y is between 0 and 1. And when y is in between 1 and 9, we can find in this circumstance that the y to the power of 1 divided by 2 is when minus y is y to the power of 1 divided by 2 is smaller than minus 1. So then in this circumstance, capital F x minus y to the power of 1 divided by 1 minus y divided y to the power of 1 divided by 2 is equals to 0. And so in this circumstance, capital F y y equals to this, and this equals to and because a and b's value is minus 1 and 3, so this equals to y to the power of 1 divided by 2 plus 1 divided by 4. And the last circumstance is y is bigger than 9. In this circumstance, we can find it's obvious that f capital Fx y to the power of 1 divided by 2 is equals to 1, and capital Fx, and this part is equal to 0, so capital Fyy equals to 1. And so we can obtain the probability distribution function of variable y, capital Y. So capital Fy y equals to 0 when y is smaller than 0, and y to the power of 1 divided by 2 when y is between 0 and 1, and y to the power of 1 divided by 2 plus 1 divided by 4 when y is between 1 and 9, and when y is greater than 9. And also because when y is equals to 0, and the capital Fyy0 is equals to 0, so we can also write the probability distribution function of variable y into this format, and this is convenient for us to calculate the probability density function. And so and also we know that the probability density function can be calculated by the by the derivative of probability distribution function. So the probability density function of variable y is equals to this. And y is between 0 and 1. This y is between and so this is the probability density function of variable y and capital Y, and in order to, and we can also draw the figure of probability density function and probability distribution function as this. And because is equals to this from the conclusions above, and so we can draw the figure, and it is when y is equals to 1, it is the probability is 1 divided by 4. So and when y is between 1 to 9, we can draw this part. and when y is bigger than 9, it is 0, and this should be y. And this is the probability density function figure. And the probability distribution function figure is this. And this because f when y is between 1 and 9, which is equals to y to the power of 1 divided by 2 plus 1 divided by 4, and when y is bigger than 9 is 1. And so it is obvious that this figure should be divided into two parts, and when y is equals to 1, and the distribution function should be equals to 1 divided by 2. And when y is greater than 9, it is equals to 1. So and when y is bigger than 9, the probability is 1. So this is the probability distribution function figure. In the last question, we need to calculate the expectation of variable capital Y. And this also should be calculated by using the probability density function, and we can find that this should be calculated by this. And plus when y is between 1 and 9. Sorry, should be y. And we can calculate the integral of these two parts, and the result is 7 divided by 3. So this is the two question.